Hello, good morning again, everyone, or afternoon or evening or middle of the night, wherever you are in the world. What we thought we would do is highlight some real successes in mission-specific scientific ocean drilling over the past couple of decades, and start with two of the really iconic expeditions. First talk will be from by Professor Joe Morgan from Imperial College London, and if there was a medal for heroes of scientific ocean drilling, I think Joe possibly would be one of the first recipients for her tenacious endeavours to get the drilling of the Chicxulub impact crater complete. So great, very warm welcome to Professor Morgan.
Okay, so as Damon just said, this was actually a pretty fantastic expedition, and I'm a bit mortified by that introduction, but I'd like to say a few things about that, in that it took a lot of effort and a lot of work, which will be fairly obvious from the talk, and a little bit of luck. So I must admit we had in some ways we were pretty lucky in what we found. So this is Expedition 364, and it's and I was one of the co-chiefs, and it was an MSP platform. And also I was asked to talk about the fact that it was an IODP, joint IODP, ICDP funded. So I'll talk a bit about that. So when I was thinking about how to plan this talk, I guess what everybody wants to know is how to write a good MSP proposal. And that sort of made me laugh, because it took 18 years for me to get this funded. But presumably I do know something a little bit more about that process now. I'm going to spend quite a little bit talking about the background drilling and seismics, because that really helped make this expedition the success it was. So in particular, when I first started to study Chicxulub, Chicxulub is half offshore, half onshore, and so there's quite a lot of onshore holes that have been drilled by Pemex, and that very much helped us with other geophysical data sort of design a seismic experiment that was targeting imaging the crater. And then those seismic data was really critical to us citing site M0077, so Expedition 364. One of the things that we had that was a big advantage was that I ran some full waveform version of the offshore streamer data, so the seismic data we collected offshore, and that allowed us to get a very high resolution velocity model that I'm going to show you today, and that did help us both better locate where to drill, and also then now to interpret the seismic data away from the drill hole. So that's really maximized our science. So both Damon and Roz mentioned having to make your objectives compelling, and I would sort of echo that. So when I first wrote this proposal in 1998, the objectives were really crater focused. So I got interested in the Chicxulub crater, and I wanted to know all about cratering, and that really wasn't good enough. And so broadening the objectives, which I'll tell you about during this talk, was really important to get community support. And actually, some of the best results we've got are from those broadened objectives, so it increased the scientific impact of our drilling. So what you're seeing here in the top left is what we currently think the crater looks like. And in the impact basin where we've drilled into the crater, there are 5 holes. So 4 of them are onshore, and the Expedition 364 is offshore. This shows the map of, so the crater's sort of in the middle here. It's overall gravity low, so that color is gravity. So blues are gravity lows. And you can see that, that's the coastline of the Yucatan coastline, and you can see that all the sort of reflection profiles are offshore, but prior to Expedition 364, all the drilling was onshore. So these are 3 Pemex holes, and this is Yashka 1 is an ICDP hole. So how does that arise? Well, partly because drilling onshore is, I've got cheap there, but I think Yashka 1 cost $1.5 million. No, actually about $1 million, and it was about 1.5 kilometers deep. Whereas M077 was about, the offshore hole was about 10 times more expensive and not quite as deep. So drilling onshore is much cheaper. And lots of people always said, well, why don't you drill the peak ring onshore? And the reason is because of seismic data. So you can see here, this is what onshore looks like, the Yucatan subtropical sort of rainforest. We were able to sort of trek into that forest to produce these, to put these seismometers down, these white dots here. But there's no way that you could do a proper seismic profile here and get a really good image. Not least apart from the fact this is jungle, because this is carbonate platform rocks, it's heavily karsted, there's lots of caves, it's fabulous potholing country. So it's really awful for collecting seismic data. The Pemex did try to acquire some, but I saw that data and it was very, very low quality. So all the seismic data, the beautiful seismic data we required was offshore. And you see there's a gap here. So basically, so in this zone here, just offshore. So here it's obviously 0 meters water depth. The drill hole's in 20 meters water depth, and it's a sort of carbonate platform. So you just get a gradual increase in water depth as you go out towards the Gulf of Mexico. So this bit's really difficult to image in because you can't really get cables in here. We put a few seismometers in here. So there's a sort of zone halfway through the center of the crater that's difficult to image. And seismic data is basically relatively cheap to acquire offshore, and it's about 10 times as expensive to acquire onshore. And it's also, in the case of Chicxulub, a much lower quality. So Pemex drilled in the 50s and 70s. They drilled actually, so this hole here, so I meant to say that this is a gravity high in the middle surrounded by a gravity low. The gravity low here, where the peak ring is a gravity low because these rocks have got a very low density, and I'll show you a low seismic velocity. And it's a gravity high in the middle here because the lower crust comes close to surface. So we've got, during crater formation, you've got dramatic movements in the crust, and the lower crust has moved up about 15 kilometers in about 10 minutes. So the Pemex drilled here because they thought, oh, this is a gravity low, and this is an anticline, and that's perfect for where oil is going to be. But clearly the gravity high was a basement uplift. They drilled into what they could see immediately was not, they thought it was volcanic. So they got into the impact breccias and thought it was probably a volcano. UNAM and ICDP then drilled in the early 2000s, and Yashka 1 was located without seismic data. And that means essentially it's very difficult then to know what happens away from the drill hole. So we acquired 2 sets of seismic data in 1996 and 2005. I wrote my first IODP proposal, I think, with about 6 holes, all about 3 kilometers deep. They must have laughed quite loud when I submitted that in 1998. And then in between in between 1996 and 2005, we spent a long time refining the proposal. And then we acquired seismic data in 2005 to collect site survey data to drill Expedition 364. And then Expedition 364 was drilled offshore in 2016. So I'm going to continue with the seismics for a little bit longer. So what does Chicxulub look like? It doesn't, I think Damon showed some beautiful pictures of the moon. You can see lots of craters there. They look similar to this one, and they had a basin, and in the middle of the basin they had a peak ring. So quite a few of the craters he showed had a peak ring, just like Schrodinger. And that's essentially what Chicxulub looked like straight after the impact. So this is our seismic image. The red line there shows, the red box shows you where it's taken from. And you can see that the basin's full of sediments. So this has basically been filled with about 1 kilometre of sediments. But at the base of those sediments, there's reflected sediments. You can see the original topography across the crater. So it would have looked a little bit like this. So some of the key things we got from that seismic data, so particularly across the peak ring, so this is the where we drilled, and this is the reflection and travel time refraction velocity model from that data. So you can see two things. One, that the velocities in here are very low relative to sort of the surrounding rocks, and that is basically consistent with that gravity low I showed you earlier. So the peak rings form from low density, low velocity, relatively low density, low velocity rocks. And directly below the peak ring was surprising as we saw these Cretaceous sedimentary rocks, and that sort of changed our whole idea of how craters were formed. So basically what we see is that the Cretaceous rocks are slumped down to form a terrace zone, and that happened during crater formation. I'm going to show you a simulation of that. And directly beneath the peak ring is the innermost sort of slumped sedimentary block. And the other thing that the velocity showed that was neat was the fact that in the middle of the crater here, so in this area, we've got very, very high velocities, velocities of lower crustal velocities, right at surface, right close to surface, so at 5 kilometers depth. So that showed us that the lower crusts had come up quite close to surface during crater formation. And then finally, I'm going to show you our full waveform image, because we're pretty excited by that. So we ran, this is actually Gail's image, which was better than mine, but we ran that before the drilling, and we used that to select exactly where to drill. And we drilled basically in this little sort of valley in the peak ring. And we drilled it there because we wanted to target these low velocity rocks. We were interested to see what they were. They actually turned out to be research impact breccia. We were hoping that this was sort of a valley that was less affected by erosional processes. So outside of in all the other drill holes, nobody's managed to get a intact sequence from the crater to the earliest Paleogene sediments. And we did, and so we was hoping that this was a place where that boundary might be intact. And yes, it was. So that was, that was one of the fabulous things about this expedition, is we managed to get that boundary sequence. And apart from using it to locate the hole, we're now using it basically to interpret the features across the crater. So we can see that this low velocity saddles the peak ring, and it goes all the way into the annular trough and into the central basin, and this is the resurge breccia. We can also, because we've got the drill holes Y6, C1 and S1, tell us that this material here is impact mount rock. So I mentioned broadening the objectives. So I said that when I originally put in a proposal, I was very interested in these two things, how are peak rings formed? What are the mechanics of peak ring formation, large crater formation, and how does it happen at all? Because for a crater to be formed, as I'm going to show you, you have to have almost no cohesive strength, and you have to reduce friction substantially to make the rocks flow initially like a fluid, so like a viscous fluid. So how that happens, how does that happen? And then as we sort of were meeting with the community and developing the proposal over sort of many years, we added sort of we added these extra targets, scientific targets in red, and those really sort of helped us sort of sway the community that this was actually a really exciting proposal. So is the peak ring, which is formed from sort of these very porous rocks. Was it habitable? Is there a deep biosphere there? And how did life recover immediately after the impact? Because this would have been a very sterile zone. We've got a superheated impact melt sheet. We've killed everything. So how does life recover actually in the basin? So yes, this was a mission-specific platform drilled in 20 meters of water, drilled with a lift boat from Louisiana that had to be slowly make its way all around the Gulf of Mexico. Can't go straight across because you can't take this boat across the deep oceans. Had to stop a few times on the way. This is how we got onto the lift boat. And the Mexicans call this the widow's basket, which doesn't really sort of encourage you to get on it, but you didn't really have much choice at that point. What did we drill? So this is the hole drilling, and this is the seismic data. This was that low velocity zone that I mentioned, and that corresponds exactly with this crater breccia. As I mentioned, one of the most exciting things was the transition from the crater deposits to the Paleogene sediments was intact, and we get a beautiful iridium anomaly right at the top of that transition. So we have a PTM, we had the transition, we had lovely breccia, and then we had 500 meters of granitic basement, which I'll show you some more pictures of that in the next slide. So I have to say we've got beautiful rocks. It was very exciting every time they came up. So the impact melt rock's pretty impressive. The crater breccia is quite impressive. What you're seeing here is lots of bits of target rocks and lots of bits of melt rocks. So the green and the black are impact melt rocks broken up into pieces. That's carbonate, Cretaceous carbonate, and then just there I think is a nice, or it's a bit of basement anyway. So everything's mixed together turbulently as part of the impact process. The granite's fabulous, and I suppose that again, lucky things that happened to us is that this granitic basement that moved essentially from about 10 kilometers below surface to about 1 kilometer below surface in, as I mentioned, 10 minutes, has nothing else deforming it. So the only deformation in this area is all impact related. So that's perfect for studying for the structural geologists. So what they see is this granitic basement fractured, very heavily fractured, and that happens as the shockwave passes through. Those fractures are cut by cataclysites, and that happens when the rocks are moving, this 20 plus kilometers that I mentioned. And then finally, they have basically, they're cut by shear zones, shear faults, which happen as the rocks regain their strength. So one of the first things we published was how a peak rings form. So once we drilled into granite and we discovered how the pressure of the granite, that shock pressures of the mineral from the mineralogy that the granite had been subjected to, we were able to ground truth our simulations. So you can see here that the blue zone here, it tells you the shock pressures, that the maximum peak shock pressure that the rocks have been subjected to. So this is where we drilled. This is where the peak ring is, and the shock pressures are consistent with the mineralogy. And also, you can see here that the sediments are directly beneath. The sediments have drown dropped to form a terrace zone directly beneath the peak ring. So that was, we were able to rule out other models of peak ring formation and decide the dynamic collapse model was correct. As I mentioned, we were sort of very interested in habitability of this peak ring. We weren't sure whether it would be habitable, because we know that this peak ring would have been at about 350 degrees centigrade initially, because it was moved upwards 10 kilometers, and when the shock wave passes through, it leaves some heat as it moves through, so that it was heated by that shock wave. And also it's sitting next to a superheated melt sheet, or not, perhaps 10 kilometers from the melt sheet. Super porous, we can see that the granite's still porous, So we would have expected sort of quite severe hydrothermal circulation all the way through the impact rocks, all the way through the crater. So yes, the peak ring, we have shown that the mineralogy shows us that there was hydrothermal circulation, and that the we can tell it lasted at least 150 years because we can see a switch in polarity from reverse to normal polarity in the geomagnetic data. And we also know that there's a modern deep biosphere that was presumably occupied those rocks quite soon after the impact. So that was an exciting discovery. I'm also going to show you that the oceans recovered very quickly in the impact basin. So that suggests that really that impact craters could be where early life may have evolved 3.8 billion years ago. So as I mentioned, we've got a fabulous transition from crater rocks. So we've got impact breccia, which was deposited by a water resurge ceasing tsunami. So because the impact crater was about kilometers deep and it's right next to the Gulf of Mexico, we'd expected water to resurge back into the crater within hours and then start standing waves. So we've got evidence for seep deposit. And finally, it looks like we may have a tsunami that's come back from across the other side of the Gulf of Mexico. So those were deposited very quickly. Then we've got this very intriguing transitional unit where the survivors increase upwards in that transitional unit relative to the reworked Cretaceous fossils. So that suggests to us that life did come back into the crater. We see this as some sort of settling zone with the waning sort of siege, and we think the sedimentation sort of increases, is quite sedimentation rates are high here but much lower up here. So we think that in the first few years we had some life here, brought in back by the resurging waters. It wasn't healthy because the fossils per gram is about 6,000 fossils per gram, whereas when we get into the Paleogene sediments, we're back up to about 90,000 fossils per gram. And we have some constraints on the timing because just here we have our iridium layer, which corresponds to the iridium label globally. Okay, so I can see I'm running out of time. I should have timed it better. We also can see that microbacteria came back into, so we've got evidence for cyanobacteria in here. So there was things surviving. And the climatic objectives were quite key to this proposal. So if we know more or less, we think direction of impact, we know what the sedimentary rocks were composed of. If we know so our numerical simulations tell us the shock pressures in the subsurface. We know from experiments how easily what shock pressures are required to degas carbonates and evaporites. So that allowed us to say more about how much sulfur and CO2 were released into the atmosphere on impact. And basically that means we would have had cooling for something like 3 to 16 years. So in the first year, reductions of about 25 degrees C on land and 10 degrees C in the ocean. Slightly new to that, we've looked at the PAH record. That seems to suggest that there's petrogenic carbon at the impact site and a mixture of petrogenic and pyrogenic carbon in the distal sites. So we think this means that some of the organic matter was converted to black carbon from the during the and ejected into part of the ejector and then circled the Earth, probably in a dust cloud, and that was made a significant contribution to the global darkness. And then soot from the impact site and the global wildfires probably produced similar cooling to the sulfur, but a more significant reduction in sunlight. So we would have reduced photosynthesis and made it likely to be sort of one of the main drivers of this mass extinction. Okay, so I rushed my last slide so that I wouldn't finish late. I think this was an incredible, successful MSP expedition. I didn't say too much about the ICDB IODP collaboration, but essentially I hope that what we did sort of was pave the way for others, in that when I first started to try to get those two organizations to talk to each other, it was quite difficult. They had very different processes. And then gradually sort of we managed to get them to talk to each other, and they ended up in this fabulous collaboration. So I think that was very successful, and hopefully other people can do the same. So yes, broadening the objectives, help get community approval, increase the scientific impact. Full waypoint inversion was very powerful for us, and it helped us pick the drill site. And if anybody after this talk wants to ask questions and don't manage to ask their question now, then please do free to contact me.
Okay, thank you very much, Joe. Still fascinating, and a wonderful example of mission-specific platforms, collaboration between different drilling programs. And also, I hope people recognize the quality of the core. Being able to mount high-speed diamond rigs on a solid platform just brings back cores that are unsurpassed in quality. Any questions for Joe? Either put them in the chat, or if you just want to unmute yourself and ask directly, that would be fine.
I would love to drill to 5 kilometers. That's Damon's.
Well, that's what I was. But that is, yeah, just to get started, that is a serious question. If you had the opportunity to site another hole, where would it be? What would be the next target?
So we would put it onshore, because
Do you think you've got all the good stuff?
Yeah, because they have drilled in, and C1 we'd put it right next to, so we know exactly what the top looks like, and then we would hopefully go through that impact melt sheet and go into the lower crust, as you mentioned. So yeah, that would be a fabulous target. So when we were doing meeting and trying to our various meetings and workshops, that was the second favorite target, but obviously it's deep, so it's more of a challenge.
Yeah, and that'd be a 5 kilometer hard rock hole, which would be quite tricky. There's some other comments coming in. Can you see those, Joe?
So I think, yeah, so the seismic data really depends on your target. I think it was really important for us because it helped us identify which part of the structure to drill, and got the community together to say, why is that important? So I think for us, seismic data was very important. But I can see for other targets, it might not be. I mean, and then I'm looking at the question.
Well, just to finish it, but in general, you will always need some form of seismic information,
yeah,
and crossing lines to site a drill site. You need to be able to prove that your target rocks are where you think they are or assert they are.
So the IODP survey, the second survey, the 2005 seismic data that we acquired, was acquired was part of an IODP fund, was IODP funded. So there was you could get at some point IODP funding to fund site surveys. So I think that was what that question.
That was UK money though, wasn't it?
Yes, it was UK money. Yeah. Then, so we got the initial bit, and then University of Texas, then managed to use that to raise more, and then Cambridge managed to raise more with a NERC grant. So yeah, it's started the whole thing.
And there will be UK IODP. Well, there's currently a UK IODP site survey call out, or just about to come out, for virtual site surveys.
Yeah. The last one, is there another impact crater that I would be interested in drilling? I don't know, this one was so good. I'd like to sort of end there. So if I haven't answered any of these, please feel free to email me if you want more details.
Okay, Joe, thank you very much for a really for your leadership of this and just this truly incredible and really exciting project.
Okay, thanks for listening.